Hi, my name is Sang-Yeon Lee, CEO of BSang Inc. You may be wondering what BSang means. It means rising high in Korean and comes from the Chinese character. Today, I'd like to share the story of 3D-IC, which includes the motivation of 3D-IC, the history of 3D-IC, and challenges associated with 3D-IC, why 3D-IC is becoming crucial to the semiconductor industry, and lastly, I'd like to tell you about BSang's True 3D-IC. I should mention that my talk will be limited to 3D-IC at ULSI, or Ultra Large Scale Integration. Some people consider 3D packaging with TSV as a 3D-IC. However, it is just wafer level 3D package with very limited 3D interconnects. Okay, come on in. Okay, let me explain the motivation of 3D-IC. Here's a picture of Seoul, Korea in 1894. Most people were living in single-story homes, and there were not many people in Seoul at the time. So they were able to enjoy the many bedrooms and large backyard. We may imagine these single-story houses as transistors on the silicon wafer surface. If we apply Moore's law to Seoul, as the population in Seoul starts to grow, people should shrink the size of their houses in order to accommodate more people within the given area. Here's a picture of a small house. We may consider this man on the porch as an electron. His wife is not shown here because she complained about the size of the house and went to the neighbors. We call this a leakage current. This real estate problem can be easily solved if high-rise buildings support enough living spaces for more people. Here's a picture of Seoul now. More than 10 million people are living in Seoul. It is difficult to imagine Seoul in the 21st century without high-rise apartments and office buildings. This is the reason why 3D-IC must be needed in order to continuously increase device density. It makes sense, doesn't it? Before I start my talk regarding 3D-IC, let me explain the category of 3D technologies in semiconductors. The first category is 3D transistor, which are small elements consisting integrated circuits. In general, billions of transistors are connected to build one IC. Conventional planar MOSFET transistors are 2D and facing limitation of device functions because the short channel effects are severe. Therefore, 3D transistors are designed to extend the lifespan of MOS transistors. The second category is 3D-IC, which is the single-chip technology implementing high-performance active devices on top of metal interconnect layers and other high-performance active devices. 3D stacking of passive devices such as stacked capacitors and poly resistors are not considered as 3D-IC. Thin-film transistors on top of glass substrate are active devices, of course. However, these are not considered as 3D-IC due to low-level device integration and poor device performance. I will explain why 3D-IC should be an ultimate solution for the semiconductor industry at a later time. For your information, BSang is the only company providing 3D-IC technologies in the semiconductor industry. The third category is 3D package with or without TSV, which is simply 3D stacking of multiple conventional 2D ICs. It is not related to Moore's law at all. It does not extend the lifespan of CMOS either. In general, additional cost is required for 3D package with TSV. However, it is a good solution for high package density for mobile devices. And 3D package with TSV could increase the performance of the system when it replaces large circuit boards and increases number of internal paths using TSV. Hi. Conventional 2D IC have transistors formed on the top surface of semiconductor wafer. In order to build 3D ICs, additional semiconductor layers are needed on the top of existing devices and interconnect layers. There are some crucial requirements for this 3D layer formation. The first one is defect-free single crystalline semiconductor layer. The second one is low temperature processing in order to avoid the disturbance of existing devices and interconnect lines underneath the forming 3D layer. 3D layer formation is extremely challenging because it is practically impossible to deposit single crystalline semiconductors on the top of amorphous layers, such as silicon dioxide film, which works as interlayer dielectric or passivation. Let me discuss these three well-known methods for the formation of 3D layers. The first one is laser recrystallization of the deposited amorphous or polycrystalline semiconductor layer. The second one is local epitaxial or laser-induced layer growth through the small openings to the single crystalline semiconductor substrate. The third one is wafer bonding and detaching method. Let me explain the laser recrystallization method first. This method is used to melt deposited amorphous or polycrystalline semiconductor layers with laser beams in order to crystallize the layers. There are two major issues associated with this method. The one is that it requires high temperature processing from the laser beam for the localized melting of the amorphous semiconductor layer. Silicon melts at around 1400 Celsius, which is high enough to alter or destroy the underlying devices. The other issue is high defect density from the uneven recrystallization. Even with recrystallization of the semiconductor layer, the resulting layer is much different from single crystalline semiconductor layer. Here is a picture of laser recrystallization. The dark area shows a crystallized semiconductor and the white lines are grain boundaries. As the number of laser beam shots increase, the grain size also increases. Because the grain boundaries are defect sources causing leakage currents and gate oxide failure, reduction of grain boundaries means better device performance. However, there are still many grain boundaries as shown in these pictures, which eventually prevents this method to be used as 3D layer formation for high performance 3D IC. Okay, let me talk about the local epitaxial or laser-induced layer growth method. Here is a picture of it. Using small openings on the semiconductor substrate, single crystalline semiconductor layers can grow. However, this method cannot avoid high temperature processing and high defect density on the 3D layer, as shown in these pictures. The white spots on this picture shows protrusions with defects. Therefore, this method is not suitable for 3D IC either. The wafer bonding and detaching method is a well-known SOI or semiconductor on insulator technology. Compared to conventional bulk semiconductor substrate, SOI has been introduced to increase transistor performance. However, it is not designed for 3D IC either. Let me explain the reasons. SOI technologies typically use oxide bonding technology because the bonding oxide layer is used for device isolation called box or bottom oxide. The oxide is summarily grown from unpatterned or blank wafers. Therefore, the surface must be super flat. However, the top of the patterned wafer surface cannot be such super flat even after CMP or chemical mechanical polishing due to dissing, slurry, particles, scratch, erosion, etc. Therefore, oxide bonding will not be suitable for the 3D layer formation. The other important problem is associated with hydrogen ion implantation for the detaching of the thin semiconductor layer from the donor wafer after wafer bonding. The dose of hydrogen is too high, and therefore semiconductor crystalline lattices are demolished by the hydrogen ion bombardment during the hydrogen ion implantation. Therefore, typically annealing at more than 1100 Celsius is required to cure the lattice damage after wafer detaching. Such high temperature processing certainly destroys underlying devices and interconnect layers. Without high temperature annealing, the transport layer should be the same as highly defective amorphous layer. It seems that there's no way to cure lattice damage at low temperatures. BSAN has disruptive 3D layer formation technology, and it enables formation of defect-free single crystalline semiconductor layers at low temperatures. 3D layer formation on top of existing semiconductor product wafers has been accomplished by BSAN for the first time in the industry. We believe that BSAN is the only company that has 3D layer formation technology. Let me explain the details at a later time. Thank you for tuning in, and see you next time.